Think you know your trees? Validate binary search tree is a pattern mastery 100 essential and a classic filter in Google, Amazon, and Microsoft interviews. Nearly 1 in 3 candidates get tripped up by subtle edge cases or misuse of recursion. Master this, and you'll be ready for any problem that tests understanding of tree invariants and value constraints. Let's use the basic approach to tackle validate binary search tree so you'll never miss a hidden bug or boundary case. Let's break it down. Given the root of a binary tree, determine if it's a valid binary search tree, BST. For every node, all values in its left subtree must be less than the node's value, and all values in its right subtree must be greater than the node's value. Input: root node of a binary tree. Output: Boolean, true if the tree is a valid BST, otherwise false. Here is a real-world example. Suppose you're maintaining a database index tree. If the tree violates BST rules, searches become incorrect or inefficient. An interviewer might ask, how would you validate a config tree to ensure proper ordering for efficient range queries? Let's assess. What's tricky? A common mistake is to just compare each node with its immediate children, but BST rules require every value in the left subtree to be less than the current node, and every value in the right subtree to be greater, all the way down. Think step by step. Use recursion with value boundaries. Each time you descend left, update the upper bound, current node's value. Each time you descend right, update the lower bound. If any node violates these constraints, the tree isn't a BST. Let's go deeper. Start with the full possible value range. Example, from -infinity to +infinity. At every node, if the value isn't strictly within min, max, return false. Recursively validate left and right subtrees, passing updated bounds. Edge cases. Duplicate values are not allowed in a BST, must be strictly less/greater. An empty tree is a valid BST. Subtle violations deep in the tree. Example is a right child of a left subtree is greater than root, must be caught. Here is the structure. Write a helper function with node, min, and max parameters. If node is null, return true. If node's value not in min, max, return false. Recursively validate left subtree, max equals node's value. Recursively validate right subtree, min equals node's value. Return true only if both subtrees are valid. Now let's implement the inorder traversal approach, ensuring the values appear in strictly increasing order to confirm the tree is a valid BST. Method start: we create a stack to manually simulate recursion. This will help us perform an inorder traversal without using the call stack. We store the value of the previously visited node. In a valid BST, inorder traversal should give a strictly increasing sequence, so this pre-value helps us detect any violations. Traversing the tree, we continue looping as long as there are nodes to visit, either moving downward through left children, or popping from the stack. This inner loop walks down the left side of the tree. In inorder traversal, left children always come first. We push each node onto the stack to return to later. And we move left until we reach the bottom. Visiting nodes in sorted order, we pop from the stack. This gives us the next node in sorted, in order. We check if the current node's value is less than or equal to the previous value. If it is, the tree breaks the BST rule. Inorder must strictly increase, so we return false immediately. We update prev to the current node's value before continuing. In inorder traversal, after visiting a node, we move into its right subtree next. Final check: if we finish the traversal without detecting any violations, the tree is a valid binary search tree. And that's how this algorithm works. It first walks the tree in inorder order, tracking values as it goes, then uses those values to verify that the sequence is strictly increasing. Efficient, simple, and elegant. Let's test our BST validation using this tree. It represents a root value 2 with 1 on the left and 3 on the right. Inorder traversal gives us 1, 2, 3, which is strictly increasing, exactly what a valid BST should produce. And that's exactly what our program outputs, true, matching the expected result. So, our implementation is correct. The tree satisfies the BST property. Now let's implement the bounds-based recursion, verifying each node's value stays within its allowed range as we move through the tree. Main method. We begin validation by calling a helper that checks whether the tree obeys BST rules. We start with the widest possible numeric range, from the smallest, long to the largest long, because the root has no initial restrictions. Validate helper method. This method ensures that each node's value stays within its allowed bounds. Every node in a BST must sit between a lower and an upper limit inherited from its ancestors. If we reach a null pointer, that means this branch is valid so far, there's nothing left to check, so we return true. We check whether the current node violates the BST property. Its value must be strictly greater than the lower bound and strictly less than the upper bound. If it falls outside this range, the tree is not a valid BST. Recur on left and right subtrees. For the left child, the upper bound shrinks, it cannot exceed the current node's value. We carry the same lower bound downward. For the right child, the lower bound grows, its values must be strictly greater than the current node's value. We keep the same upper bound. And that's how this algorithm works. It first assigns each node an allowable range of values, then recursively narrows those bounds as it descends the tree. Efficient, simple, and elegant. Let's test the BST validation again with this input. Here, node 4 appears in the right subtree of 5, but it contains a left child 3 that violates the BST rules. In a valid BST, every value in the right subtree must be greater than the root. But 3 is less than 5, so the structure breaks the BST property. And that's exactly what our program returns, false, matching the expected answer. So, our implementation is correct. It correctly identifies this tree as not being a valid BST. So, how do you really know if a tree is behaving like a proper binary search tree? Validate binary search tree is the perfect check of whether you understand how recursion and constraints flow through a tree's structure. Let's do a recap. The problem asks us to confirm if a given binary tree follows BST rules, meaning every node's left subtree has smaller values, and every right subtree has larger values. Conceptually, it's about keeping the entire structure ordered, not just comparing neighbors. We discussed how many people slip by only checking parent-child pairs. The trick is realizing that each subtree inherits boundaries from its ancestors. As we move down, we must update those value limits, shrinking the valid range for each recursive call. Our logic was simple but powerful. Start with a wide range, say from negative to positive infinity. For each node, verify it fits within that range. Then, move left with an updated upper bound and move right with an updated lower bound. The recursion ends cleanly when all nodes fit their limits. We coded this recursive check, starting from the root and passing updated boundaries as we traversed. The function neatly returned true or false depending on whether every node respected its constraints. Running the solution on LeetCode confirmed it works perfectly. Valid BSTs passed as true. Invalid ones returned false, and tricky edge cases, like deep violations or empty trees, were all handled correctly without errors. The key takeaway: a valid BST isn't about direct neighbors, it's about inherited rules. Mastering that recursive boundary mindset ensures you won't miss hidden violations buried deep in the tree.